Hey everybody. We're going to wrap up today talking about the three types of spectra. So far we've been talking just about the first type of spectra, a continuous spectrum, or a blackbody spectrum. Remember, a blackbody spectrum is what you get from a hot, dense object, where that hot, dense object gives you your blackbody spectrum. It gives you an emission of light at all wavelengths all the way across the spectrum, but what wavelength is brightest depends on the object's temperature. And so by observing the color and the peak wavelength in a dense object spectrum, you can determine what temperature it must have. There are some things that you would want to know about objects like stars, nebula, galaxies, planets, that you can't know from just the continuous spectrum. So that's where our second and our third types of spectra come in. The second type of spectra, the emission spectrum, is what you get from a hot, low-density gas. So why does a hot, low-density gas give you a different kind of spectrum from a hot, high-density object? And it has to do with the way that gases and light, low-density gases and light interact. Because with a low-density gas, there's a lot of empty space in between all the molecules, and that means the light can get into the gas, and the gas molecules and the light can interact one-on-one. And that causes the spectra to be different. So in order to understand what a hot gas is doing, we need to talk about gases, and that leads us to talking about the atomic structure. So, quick recap. Right? What is an atom? Well, an atom is an atomic nucleus made up of protons and neutrons, surrounded by and orbited by the electrons. And in your typical cartoon of an atom, it looks like you've got this atomic nucleus with the electrons orbiting around it the way planets orbit the sun. This is usually the way that we sort of draw it, but that's pretty much nonsense. Right? Electrons are way too small, they're moving way too fast. You can't watch an electron orbit around an atom as if it were some large, slow-moving planet moving around the sun. It's a lot more realistic to say that an electron is zipping around the atom in some hazy, diffuse cloud, where you can't say exactly where the electron is at any given time, but you can say probably it's in this neighborhood. It's a lot more realistic to say what the probability of finding an electron is at certain locations moving around in the atom, because you can't pin down exactly where the electron is at any given time. Which is a problem if you're trying to figure out everything about atoms, but for our purposes here, this isn't that bad, because we don't care where an electron is at any given time. What we care about is the energy, and that you can pin down. So let's look at the energy of electrons in an atom real quick. So let's start really basic. Let's start with the simplest atom you can get, hydrogen. One proton, orbited by one electron, and let's start even easier and let's say, okay, this electron can only be at two energy states. The electron can be at a lower energy level or an upper energy level. That's it. If you remember your basic chemistry, electrons can only exist in atoms at specific discrete energy levels, right? In this case, the electron can be at the lower energy level, the upper energy level, that's it. Nowhere in between. If the electron can only exist at two specific energy levels, how do you go from the lower energy level to the upper energy level, right? Everything in our universe tends to want to settle down into the lowest possible energy state, right? Our universe is a fundamentally lazy place where everything wants to sort of be at the lowest, most relaxed ground state. That's the name for the lowest energy level that an electron can be at, the ground state. So left to its own devices, this electron will just be at the ground state, it'll be at the lowest energy level, and it'll just stay there. How do you get an electron excited? That's what the electron is called when it's in the upper energy level. It's in an excited state. It's at a higher energy state. Well, one way to get an electron excited is heat the atom up. If you take a whole bunch of these hydrogen atoms, if you take a whole nebula of these hydrogen atoms and heat them up, well, what's going to happen to the atoms? What happens to a gas when you heat it up? The atoms start moving around faster. They're going to start moving around and colliding with each other, and as these atoms collide with each other, they're going to exchange energy, and that means that when two atoms collide with each other, one of those electrons is going to absorb some energy, and it's going to jump up into the upper energy state. So it'll be up here in an excited state. And electrons can stay excited for a little while, a few seconds, maybe a few minutes, but typically they don't stay that way. Inevitably, an electron will relax back down to the ground state and it'll lose that energy. How does an electron lose energy? The energy can't just disappear, right? Energy has to be conserved, so that if the electron is losing energy, the electron goes from the upper energy level down to the lower energy level. That electron is losing a specific amount of energy. How does it lose that energy? By firing off a photon. It's going to shoot out a photon of light, and that photon is going to carry away exactly the amount of energy that the electron lost in going from the upper energy level down to the lower energy level. So that the total energy of the electron plus the photon is conserved. The electron loses energy by shooting out a photon to carry away the energy that it loses. What's another way that the electron could get excited? Well, if you start off with an electron in the lower energy level, in the ground state, well, if a photon comes in, it hits that electron, the electron absorbs that photon, it gains the energy from the photon, and in gaining that energy, it jumps up to the upper energy level. So that's another way. So electrons can jump up into higher energy levels, either by absorbing photons or in a collision because the atoms are moving fast and colliding hard and exchanging energy. So let's take our hot gas. If I take a gas and I heat it up, the atoms are moving fast, they're colliding furiously and frequently, and those electrons get excited. They hang out in the excited state for a few seconds, and then they drop back down to the lower energy level, because everything in the universe wants to relax like that, and it shoots off a photon. And when those atoms all start shooting off photons, my cloud starts to glow. I've created light. The thermal energy of this hot gas has turned into radiative energy. It's turned into photons, light, given off by this glowing hot gas. Here's the thing. Because this electron can only be at certain discrete energy levels, that means that this photon that gets created can only have certain amounts of energy. So let's take a little bit more of a realistic example here. Let's say this electron can be at 3 energy levels. And if the electron is at level 1, it has an energy of 4 electron volts. What is an electron volt? This is a unit we haven't used before in class. Let's put it this way. An electron volt is a unit used for measuring energy. Let's just leave it at that. Okay, so if the electron's at level 1, it has 4 electron volts of energy. If the electron is at level 2, it has 8 electron volts of energy. If the electron's at level 3, it has 14 electron volts of energy. Okay, so if there are 3 energy levels that this electron can be at, how many different ways is there for an electron to lose energy? How many different transitions are there from a higher energy level down to a lower energy level? Think about that for a second. So if you're trying every possibility, you should realize that there are 3 possible transitions for the electron to lose energy. The electron can either go from level 2 down to level 1, from level 3 down to level 2, or to go from level 3 directly all the way down to level 1. So if the electron does this, if the electron goes from level 2 to level 3, from level 2 to level 1, how much energy has it lost? It's lost 4 electron volts. From 8 to 4. If the electron goes from level 3 down to level 2, it's lost 6 electron volts. And if the electron goes from level 3 all the way down to level 1, it's lost 10 electron volts. If the electron does this, what kind of photon gets created? Well, remember, the photon that gets fired off has to have exactly the same amount of energy as the electron lost. So if this atom I just made up, if the electron goes from level 2 down to level 1, it has lost 4 electron volts, which means the photon that gets created has to have 4 electron volts. If the electron goes from level 3 to level 2, it's lost 6 eV, so the photon that gets created, has to have 6 eV of energy. If the electron goes from level 3 directly all the way down to level 1, it loses 10 eV of energy, which means the photon that gets created has to have 10 electron volts of energy. So because there are 3 possible paths, because there are 3 possible transitions for the electron to lose energy, this atom can only create 3 energies of photon, 1 for each transition. Now, what determines the energy of a photon? It's the frequency. So if this atom can only create 3 energies of light, this atom can only create 3 specific frequencies, which corresponds to 3 specific wavelengths of light. This atom is not going to give off light at all wavelengths across the spectrum the way a blackbody does. This atom can only give off 3 specific wavelengths that correspond to those 3 specific energies that the electron is allowed to lose, based on its energy levels. So if I take this atom, let's say, I take a whole nebula full of these atoms, I heat it up, the atoms start moving fast, colliding hard, the electrons jump up to level 2 or level 3. They hang out there for a little bit, then they de-excite, meaning they drop down to a lower level. This atom and all the atoms in this nebula are going to start glowing, but they're not going to glow with all colors. They're only going to glow with those specific 3 colors. The color that corresponds to 4 eV, the color that corresponds to 6 eV, and the color that corresponds to 10 eV. So if I take all the light from this hot glowing nebula that I created, I take this light, I shine it through a prism, I break it up into the spectrum, this is what the spectrum's going to look like. I don't get all the colors of the rainbow. I just get those specific colors. These specific colors, each color corresponds to a specific wavelength, a specific energy, a specific transition, a specific way that the electron lost energy. This is what's called an emission line spectrum. Specific bright colors against a black background. Here's the awesome thing about that. Every element in the periodic table has different energy levels. And if every element in the periodic table has different energy levels for those electrons, that means when those electrons drop down and lose energy, they're going to give off different specific energies of photons, different specific colors, which means every element of the periodic table gives off a different pattern of bright lines that are unique to that element. So this is like a fingerprint, right? Every helium atom in the universe, when you heat it up, it gives off this one red wavelength, this one yellow wavelength, these two greens, these two blues, that's it. So if I look at a nebula out there in the universe, I take the light from the nebula, I shine it through a prism, I look at the spectrum. If I see this one red wavelength, this one yellow, these two greens, and these two blues, I know there's helium, in that nebula. Whenever you heat up sodium, you get these two specific yellow wavelengths. That's it. Whenever you heat up neon, it gives off a whole bunch of red, orange, and yellow wavelengths, and that's it. And so by looking at that pattern of lines, you can figure out chemical composition. You can figure out what gases are in that nebula, even if it's all the way across the galaxy, even if it's in another galaxy. By taking the spectrum of a hot gas and identifying which elements those patterns of lines correspond to, you can figure out what that object is made of. This is how we know what things are made of in the universe. When you start having molecules give you a whole bunch of lines, because in a molecule the electrons can be at a whole bunch of different energy levels, and therefore you get a lot more complicated patterns of emission lines. So when you start looking at objects in the universe that have molecules, then things get a little hairier, but it's still the same principle. Take that pattern of lines, match it to what atom or what molecule gives it off, and you know that that substance, that chemical, must be in your hot cloud, in your hot gas. This top spectrum here is probably the most important emission spectrum, because this is the emission spectrum given off by hydrogen. And hydrogen is the most abundant element in the universe. So you always know if your hot gas has hydrogen, because hydrogen always gives off this one red wavelength, this one blue wavelength, these three violet wavelengths, and that's it. If it's hot, because if the gas is hot, then the electrons get excited, they lose energy, they give off light. What if your gas is cold? Well, if your gas is cold, then, to flip back here a minute, if your gas is cold, then all of the electrons are already in the lowest energy level. They're already in the ground state. So they can't lose any more energy. They're already at their minimum energies. They can't lose any more energy. So they're not going to give off light if your gas is cold. But if the gas is cold, then all of those electrons at their lowest energy mean they are super willing and able to absorb photons in order to gain that energy and jump up to a higher energy level. So a cold gas is like this scenario here, where that cold gas will absorb photons in order to jump up to the upper energy level. Here's the thing. Because these atoms only have specific energy levels, that means only specific energies of photons are able to get absorbed. So if this is our atom again, this atom can only absorb light that has 4 eV, 6 eV, or 10 eV. That's it. Because if the atom absorbs 4 eV, that electron will go from level 1 to level 2. It can absorb 6 eV so that an electron at level 2 can get up to level 3, or the atom can absorb 10 eV, a 10 eV photon, so that the electron can go from level 1 directly to level 3. If there are 3 possible transitions between energy levels, this cold atom can only absorb 3 specific energies of photon, which means it can only absorb 3 specific wavelengths of photon. So let's go here again. If I take a cold cloud of hydrogen, and if I shine, move my face out of the way here, if I take all the colors of the rainbow, and if I shine all of those colors, if I shine a perfect black body spectrum into this cold cloud, that cold cloud of hydrogen is going to absorb light. But it's only going to absorb this red wavelength, this blue wavelength, and these 3 violet wavelengths, and that's it. all of these other wavelengths, they don't have just the right amount of energy to take an electron from a lower energy level to a higher energy level. And if they don't have the right amount of energy, they can't get absorbed. So all of these other colors of the spectrum, they pass right through the cloud unabsorbed. The only light that can get soaked up is the light that takes the electron from a lower level to a higher level. This third kind of spectrum here, this is what you call an absorption spectrum. So that's our third kind of spectrum. An absorption spectrum is what you get when a continuous spectrum, a blackbody spectrum, shines into a cold cloud, and that cold cloud absorbs out specific wavelengths and lets the rest shine on through. This is how we can figure out what we're looking at in the universe, by looking at these three types of spectra. So, let's say you discover a brand new object. Nobody knows anything about it, you just discovered it. So you find a brand new object and you say, well, I want to know about it. You take the light from that object, you collect it in your telescope, you shine it through a prism, and if that object gives you a perfect rainbow, you get all the colors of the spectrum, well, you say, aha, well, that's a continuous spectrum. What kind of object gives off a continuous spectrum? A hot, dense object does. So whatever my mystery object I just discovered is, it has to be a hot, dense object. And what else can we figure out about it? Well, that the peak wavelength right there is determined by the object's temperature. So I now know not only is this mystery object hot and dense, I now can tell you what its temperature is. If I take the light from my mystery object and I look at the spectrum and the spectrum only gives me specific wavelengths, well then I know that's an emission spectrum. What gives off an emission spectrum? A hot gas. So my mystery object must be a hot, low-density cloud of gas. But if I take my spectrum and I get all the colors of the rainbow except, if I get all the colors of the rainbow except for those dark lines, then I go, oh, what kind of object gives that off? What kind of object gives off an absorption spectrum? Well, it's a hot, dense object shining through a cold gas, and then the only light that I'm getting in my prism is the light that didn't get absorbed. So you're getting all the colors of the rainbow except for those dark lines, except for those colors that got soaked up by the cold cloud. And what determines the lines that get emitted, or what determines what lines get absorbed? It's the chemical composition of the gas. So that based on, in the case of an emission spectrum, I can tell you how hot it is. It's really, really hard to figure out the temperature of an object from the emission spectrum. It's not as easy as with a continuous spectrum. You know it's hot because it's giving off an emission spectrum, but how hot? Hot enough to be an emission spectrum. Beyond that, it's hard to tell. Not impossible, just harder. I know it's hot. If you see that your mystery object is giving you an absorption spectrum, well, you know you've got a hot, dense object, and shining through a cold cloud, and you can figure out what the chemical composition of the cloud is, based on the lines that are getting absorbed. So the absorption spectrum really is the best of both worlds, because with an absorption spectrum, you can take the peak wavelength in the blackbody spectrum, it'll tell you the temperature of the source, and the lines that get absorbed, they tell you what the chemical composition of the gas is. So the absorption spectrum can tell you both chemical composition and temperature, whereas the continuous spectrum can only tell you about temperature, and the emission spectrum can only tell you about chemical composition. This is how we can figure out composition and temperature in the universe, from looking at which of those three types of spectra the object is emitting. So if you look at something realistic, we've been talking about made-up atoms with made-up energy levels that I was creating an example for here, but in a realistic setting, if you take a realistic hot nebula out there in the galaxy, no nebula is made up of just one kind of gas. They're all mixtures. And consequently, if you have a mixture of different elements in your nebula, you're going to get a mixture of different emission lines. So here is a graph of brightness versus wavelength for a typical hot gas, for a typical emission nebula out there in the galaxy. And so as you can see, this gas is giving you a mixture of different emission lines. You're getting emission lines from oxygen, neon, hydrogen, nitrogen, sulfur. Why? Because that nebula must be made of a mix of oxygen gas and neon gas and hydrogen gas, etc., etc. And so this is how you can figure out more complicated systems out there in the galaxy, is to say, well, if I'm getting a mixture of emission lines, it must be because this is made of this, and this gas. And you can then build a recipe. You can build the recipe for this nebula must be made of oxygen and neon, hydrogen, nitrogen, and sulfur, because I'm getting all of those patterns, all of those emission line patterns mixed together. When you look at the sun, the spectrum of the sun looks like this. Which of our three kinds of spectra does the sun give you? It gives you an absorption spectrum. So we were talking the other day about how, oh, stars give you a blackbody spectrum. Yeah, that's true, but it's more complicated than that. Stars actually don't give you just a continuous spectrum. Stars give you an absorption spectrum because a star, most stars anyway, stars like the sun, are a hot, dense core giving you a blackbody spectrum, but the outer layers of the star are cooler and less dense. The outer atmosphere of the sun is a cool, low-density gas, and what does a cool gas do to light? It absorbs it. So that's what these dark lines are. These dark lines are the wavelengths of sunlight that got absorbed by the outer atmosphere of the sun, and so those wavelengths didn't escape out into space for us to see them here on Earth. And which dark lines you see can tell you what? What does an absorption spectrum tell you? It tells you chemical composition. This is how we know what the sun is made of. Because you look at the darkest lines, like this line here, this line here, that blue one there, right? All of the darkest, widest lines in the sun spectrum are from which element? Hydrogen. This is how we know the sun is mostly made of hydrogen. The second darkest lines in the sun spectrum, like this yellow one and that green one, those are from helium. And so that's how we know that helium is the second most abundant element in the sun. And all of these other minor lines are from elements that are in small quantities in the sun. Carbon, oxygen, iron, things like that. This is how we figured out what the sun was made of. You can't figure out chemical composition just from the continuous spectrum. Continuous spectrum only tells you temperature. So we know, because the sun is brightest in the green-yellow, the sun has a temperature of 5800 Kelvin, but it's those dark little lines in the spectrum that say, not only is the sun this temperature, but it's also made of mostly hydrogen, a lot of helium, and then small amounts of carbon, oxygen, etc. This is how we can figure out more about hot gases and cool gases, more over and above what we can get from just the continuous spectrum. And once you know what things are made of in the universe, then you can start asking the even deeper question of, well, where did it all come from? Where do stars come from? How are stars born? Once you've got a handle on what they're made of, then you can start putting together an answer, which we'll get to in a few days. Thanks, everybody.